Hello everyone and welcome to another session of our digital redays. My name is Silas and I will moderate this webinar today. We are very pleased that you took the time to participate in our next session. The topic of today is ICLED, the revolution of lightning control. Our speaker today is Carlos Hernandez. He is working as a product manager at Würth Elektronik eiSos. Carlos, good morning.
Good morning.
Cool to have you here.
Thank you.
Before we start with the webinar, I would like to give you some more information. First of all, you will be muted during the webinar. This means that you cannot ask us questions via your microphone, but you have the opportunity to ask your questions all the time with the chat function. Today's webinar will be about 30 minutes long, and after that we make a short Q&A session and Carlos will answer your questions. If we are unable to answer all your questions live within this time, we are answered them via email in the next days. So last information from my side, you will all receive the link to the presentation as well as to the recording in the next days via email. So now I will hand over to you, Carlos, and I wish you an exciting webinar.
Good. Thank you, Silas, for the introduction. Hello and welcome everybody to this presentation about ICLEDs. My name is Carlos Hernandez and I'm the product manager for these products. A little bit of my background. I have a bachelor's in mechatronics and a master in applied photonics that I did here in Germany. First of all, I would like to start a little bit with introduction about what's light. Light itself is the electromagnetic radiation at a particular wavelength, meaning I have two parameters to describe light, meaning the frequency and the energy. The higher the frequency, the higher the energy of the wavelength. As you see, the electromagnetic spectrum is composed or looks from under 1 picometer up to 100 millimeter. But what's interesting for us would be the spectrum, the visible spectrum and the non-visible spectrum in the UV and ER region. Why? Because this is part of the medians range of the LED technology. Now, to LEDs, what it is basically semiconductor materials that are doped to create either a positive or negative material. Joined together, these p-n sides could create a depletion zone in which there's a non-conducting layer that it's composed by the recombination of electrons and holes from the materials. Whenever we apply reverse bias, so we connect the positive to the negative side, so the positive of our battery to the negative side of this junction, the LED is not going to flow. There's not going to be a flow of energy, flow of electrons, therefore there is not going to be any flow of energy. Now, on the other side, when applying forward bias, you will see that there's this process of recombination electron holes, therefore creating light in this case, so emission of wavelengths. Okay, now we had from our portfolio the analog RGB LEDs, meaning I have one component with 3 chips inside of it. And the challenge when trying to do complex color mixing circuits or, for example, individual pixel control was that the user, the designer, or the engineer had to apply an IC to the LED, to every single LED in the circuit in order for them to control them as desired. Now, over the last couple years, the technology has been changed and evolved so that we can put this IC, it's going to be compressed and reduced in size, that it can fit inside the LED lead frame. Meaning I have an IC LED or rather an RGB LED with an IC inside. You see the 3 chips, red, green, blue in this case, are in the component, and the IC that was outside before is now in the component. Okay, in the market right now, there is not just one name in order to know this product. This product is rather known under addressable LED, intelligent LED, smart, pixel, digital, or even VOS LED. These all names are synonyms for the ICLED that we're naming. Now, how to define or how to differentiate between an analog and an RGB LED. First of all, from the general view of the component, you will see the IC. If the lens is water clear, you can see the connection, the small box inside the component, but also from the schematics, you can also see that your LED chips are connected and there's either one common anode connection or single connections for every single chip. In the case of ICLEDs, you will have a voltage connection plus your data in and data out for the IC communication. Not only that, this name a single wire LED, there is also a second version with dual wire LEDs, meaning you have a separate data and clock line in the LED. How does it work? The control of the single RGB chips is done via PWM, meaning pulse width modulation, in which the variable that is going to change is the duty cycle, or rather the time rate that is going to be on from the signal period, from the given signal period. Meaning the higher the duty cycle, the brighter the LED is going to be. Now, for the single wire communication protocol, you will see we have a 24-bit pattern to define the GRB data. This is not fixed. This can also vary from RGB, BGR, GBR, any possible combination. This is mostly dependent on the place, how much place do we have inside the lead frame to center the LED chips and connect them to the IC. So in our datasheets, you will also find this information with this type of diagrams. Now, typically, we have a bit pattern to follow that the microcontroller should create or represent in order for the IC to differentiate between bit zeros and bit ones. Meaning it's just a combination of high and low times which define the code that is going to be read out. At the end of the code line, after filling my 24-bit patterns for every single LED in my circuit, I need a reset code in order for me to define a new color combination. And important to mention, the data in the LED is transferred with most significant bit first. As mentioned before, for bit recognition, the microcontroller should fill out these patterns, and to start a new data line, you will have to send a reset code. Now, for the transmission method, how is the information going to go from LED to LED? We go once again with this 24-bit data composition. Your microcontroller, it's going to always be in the circuit, and then you have the LEDs connected in daisy chain. Now, just as an example, okay, I will send 100% of red to every single LED. I send 24 bits for every single chip or LED in the circuit. And the LED is going to take the information and it's going to light up accordingly. Now, that's the best part of ICLEDs. You don't always have to display the same color in the line. Rather, you can use color combinations. You can set different colors. You can even set one LED off, on. That's independent. Now it's just the user who defines what is going to be displayed. Therefore, making it easier to create complex algorithms or even display complex color combinations. Our advantages with our ICLEDs, we offer the MSL3 for most of our products, and the one with MSL5A has IPX wire protection. We also are interested in offering the best materials for the plating of your LED with a better solderability and high reliability, and also our delivery time is always between 8 and 14 weeks. Now, for the application, I will describe today the ICLED feather wing that probably you have seen either in our social media or during our last conferences and fairs in which were here it's described a high density LED display in the featherwing standard. This is a 4-layer PCB, which is also powered by USB-C. You will see here a little bit of the diagram, a schematic of the construction of the PCB. Important to mention, the size of the board is 0.98 times 2 inches. So we still keep the 105 LEDs in this feather size. And we can even use 1.8 volt microcontroller logic outside this featherwing standard. Important here are the parameters, so general parameters of the board. You will see on the right side a picture of the actual prototype that we're working on. Here it's important to mention we have the supply voltage from 3.3 minimum required for the board, and the minimum logic level would be 1.65 volts. The power consumption at maximum power is 8 watt, but limited at 2.5 if you want to use the software that we're offering as well. The meeting power density, 16,000 candela per square meter or nit, and a sleep current of 19 milliamperes when all LEDs are off. The frame rate can be changed if the user changes the delay time for the animations, but the maximum frame rate would be defined at 150 Hertz. Now, from the connection of the board, we have the standard feather connector with 28 pins, USB-C power supply, 5 volts and 3 amperes. We have extension pins to connect more displays together. You have the JP1, JP2, and we also included some reset pins and interrupt pins to change animations or even reset the board directly. Now, if we go a little bit inside the board, you will see that we included here the level shifter optimized for logical voltage between 1.65 and 3.6 volts. We also included the EMC filters for each VDD line of the USB-C connector. You have the resistors to drive out 3 amperes from the USB power source, maximum 3 amperes. And also we added fuses as protection circuit for each VDD line in order for us to avoid overheating of the board or undesired high currents. Lastly, we also included a TVS diode for protection against voltage spikes. From the software, we used a Feather M0 microcontroller. You will see the board is a little bit small, so you will see here on my hand. Now, later in the application, I'm going to describe you. I'm going to show you how the board works. But here's just the explanation what's happening inside the microcontroller. The microcontroller will send these bit patterns defined by our defined code, and you will see the timings generated are done via SPI and DMA, meaning with the SPI we create 4 bits in order for us to reach the timing. So you will see here as example, the bit 1 is composed by 880 nanoseconds and 280 nanoseconds in the load time. If you remember from the previous slides, we have a typical timing of 900 and 300 nanoseconds. Therefore, we are inside these tolerance ranges given in our data sheets. About the software, our library is done in C++, in Visual Studio combined with the Platform EO extension. As I mentioned before, we have the signal generation via DMA and SPI. We included an HSB to RGB color system and vice versa. We have the PWM restriction to prevent from overheating, and the program change via the interrupt possible. Also, we already coded letters, numbers, animations, so that we make it easier to the user for their quick prototyping with this board. From the implemented restrictions about thermal safety. Why we did it is because according to the recommended touchable temperatures for the ISE 62368, we define the maximum touchable temperature at 85 degrees. If you see in the picture on the right, the temperature on the board rises up to 150 degrees at 100 pwm. That means we have to limit the amount either of the PWM or the current that is going to flow through the LEDs. This is why we implemented a software restriction that the maximum PWM, the sum of the RGB chips, is defined at 210, and the fuses that I mentioned before. Now, after these restrictions, you will see that the board, the maximum temperature on the board is lowered down to 76 degrees, meaning almost a little bit less than the half of it. So if the user wants to use the board at the maximum power, they will need to include some cooling system to avoid the LED, to keep the LED efficiency in this case. Now for the use cases, you will see the program sequences that we have, for example, as a price tag to show the humidity. We have even logos program or even a rainbow animation that is going to scroll through the board. How does it look like and how we're going to show it right now? We have some example functions. So init show rainbow, show price. This is everything included in the library. And more importantly, we also can combine this display with our temperature, humidity sensors, 3-axis sensor, and even via Bluetooth, we can display some text. How does the code look like? It would be on your right side of the screen. And now I'm going to go with the feather wing. So if we connect it here, 1 second. Now, you will see the display is going to go to scroll through, or the LED is going to scroll through the whole display. This is our simple test on the functioning. Now, as you see, we included some logos, some scrolling text. If you see, we have a feather stack with the sensors and the Bluetooth module. This is our microcontroller. So whenever we change the direction of the board, the text is going to be in the same direction. This is not going to change. Now, when scrolling over, oops, there. So you will see the rainbow scrolling through the board. We also have the price tag included. As you see, it's not only fixed text, it can be also dynamic text. We go through the next animation. Some emojis, for example, can be also displayed. Now we're reading out information from the sensors in the sensor board or on the sensor board. As you see, you have the humidity, relative humidity values. And here is the Bluetooth module. So the LED or the microcontroller is going to read out the information. It's going to keep sending this send BLE data. And when the data is received from our Proteus Connect application, then you will see the text is going to change. I'm going to send the second payload. So, 1 second. Yeah. There. Oops. So, if you have any questions about the software, just in general idea, you will see here, we build up small test cases, and we have our CPP and H files accordingly. Now, with this, just to finish, you will see this portfolio for ICLEDs that we have right now at the moment, and the applications for this type of LEDs. And with that, I say thank you very much for your time. If there are any questions, feel free to ask. That's it.
Okay, thank you, Carlos, for the interesting presentation. Now we will come to your questions. Before we start with the Q&A session, I will share the handout from the presentation today. Now you can download it on the right side on the black button. Then I would say, first question. Will the ICLED feathering will be available for customers? Where can we find this?
Yes, the feathering is going to be available. We also will put it on our website, so please keep checking our website around the Q3. Our objective is to release the board before Electronica, including the programming as well on GitHub.
Okay, thank you. Then I think we continue directly with the next question. Are you tending to achieve the MSL level 1?
In this case, MSL level 1 is only achievable for THT LEDs due to the encapsulation inside of it. The maximum MSL achievable is around 2A. But for ICLEDs, it's typical that the MSL offered is 5A. So with our MSL 3, we're offering the best MSL in the market at the moment.
Okay, thank you. There are a lot of questions, very cool to see. So now we can directly continue with the next question. How many ICLEDs can be controlled in the same circuit? What would be total data transmission time?
Okay, can you repeat this?
Yeah.
Okay, good. So I prepare a slide for this situation. Give me just 1 second, then I can go through it.
No problem. Yeah. One moment, Carlos will share his presentation.
Yeah. So in this case, if you have a single wire ICLED, I'm just going to scroll through it. You will have to take into account that you have the timing of one LED times the amount of LEDs you have in the circuit. Here, the delay times between LED to LED are around 200 or under 200 nanoseconds. So we can just take these values out of the equation. As you see, you will have 24 bits time 1.2 microseconds. This is typical. It would be around 29 microseconds time the amount of LEDs in your circuit plus the total transfer time. And with that, you can have the timing of your whole circuit, meaning the more LEDs you have, the longer it's going to take to control, to see a difference between the first and the last one.
Okay, cool, thank you. Then, next question. Can the ICLED directly be driven from a 3.3 volt microcontroller?
So in this case, we're actually in the limits of the technology for LED. Yes, it can be, because an IC can be controlled at 3.3 volts, but we will need some voltage difference, a little bit more voltage for the LED chips. Okay, the technology for green and blue is around 2.9 to 3.4 volts, more or less, and therefore if the chips that are being used inside the LED have a higher voltage, higher forward voltage than 3.3 volts, then the situation is that the LEDs won't work or won't light up. And this is not our goal. In this case, as you see, the 2020 that we have in the feather wing, it's a 3.3 volt controllable LED. For other parts, they are typically around 3.5 volt for packages of 50-50 or 5 x 5 millimeter.
Okay, thank you. Then, next question. What other LED packages are planned? Anything different from what is already on the market?
For the moment, we have planned typical sizes and packages offered in the market. We want to introduce the product to that the customers know that we are offering the highest quality at the market at the moment. Exactly. If there are any requests about packaging, please feel free to contact our ADMs or contact us on the website directly, and then we can check your inquiries personally.
Okay, thank you. Then, next question. What is the maximum distance between two ICLED if they are connected via wires?
So the maximum distance is not defined. Typical values around 1 to 5 meters, more or less, but this depends on the losses that you have through your wire, meaning the higher losses, therefore the shorter the distance. In this case, important to note that the waveform for the bit recognition, as you see here in the picture, is still kept so that this is not deformed, and also that the VH height, the high voltage, is compliant with the tolerances given in the datasheet around 0.7 times the input voltage on the LED.
Okay, thank you. Then, next.
This
one.
Weiter.
How are the current gain bits of the 1, 3, 1, 2, 1, 2, 1, 3, 2, 0, 4, 3, and 7 used?
So this is a special part of 2121 PLCC6. In this case, for these LEDs, we have just the possibility to control the duty cycle of the PWM signals. For this 2121, we have also the possibility to control the current that is going to flow through the LEDs, meaning case feather wing, we have a fixed current, 5 milliampere per chip. On the other one, we have 20, but a 4-bit current gain. So we can even select and change the current that is going to flow through LED if we require lower voltages or lower power in our circuit.
Okay, then next question. The website states ICLEDs offer compatibility with open source libraries such as FastLED for fast design. Please, can you share an example for fast LEDs as this type is not supported type from the website? In this case, I can just answer it shortly. You can also download the FastLED library and go through the examples of that. You can use the ESP32 microcontroller, for example, or Arduino Uno. The only thing is connect the LEDs to voltage and the in pin to your microcontroller, the output, the in of your microcontroller. And if there's even if this is not completely clear, feel free to ask us, contact us through our website, and then, as mentioned before, we can go through your inquiry personally. Okay, then. One last question, often bare silicon diodes are susceptible to interference to the light. For example, WL-ICLEDs. Is it the IC inside the LEDs also susceptible to light interference, yeah. And if not, what precautions have been taken to protect the die?
So in this case, you don't have the open silicon die with it. You have as packaged. So the IC is packaged, and this package is not transparent, so light is not going to be going into the component. Therefore, it's safe in this case.
Okay, thank you. Then I would say it's the end of the session. When you have any questions, any more questions, then you can write into the chat, and then Carlos will answer them via email in the next days. So now, Carlos, thank you for all the answers of the questions, and for also the very interesting presentation.
Thank you.
And yeah, I hope you enjoyed it. Hopefully we see us on the next Digital Reday session. And now I would say thank you and goodbye.